Module 2, Limits and Rates of Change, Part 2. We begin with an engaging context. Many graphic design tools allow creators to scale common shapes, such as a square. When the side length of the square changes, the area of the square also changes. Recall that the area of a square A is equal to the square of its side length L. In the example, we see that we have a square with side length 2 centimeters. Because 2 centimeters times 2 centimeters is 4 square centimeters, the area of this square is 4 square centimeters. We denote the area in the middle of the square. Your first learning task is to consider a square with side length 2 centimeters with the area of 4 square centimeters, the square we just looked at. Our question is, if the side length is increased by 1 centimeter, by how much does the area change? And what is the average rate of change in that area? You can see I've redrawn the original square with side length 2 centimeters, marked in blue, and we've expanded that area as we've increased the side length from 2 centimeters to 3 centimeters. In the green shaded region, those two rectangles and that one square represent the change in the area. So pause the video here and go ahead and work the learning task. Your solution should look similar to what we have on screen. We know that when the square has side length 2 centimeters, increasing the side length by 1 centimeter increased the area by 5 square centimeters. We can see that increase because the square, or the rectangle rather, in the lower left had height 1 centimeter, width 2 centimeters. That gives us the 2 square centimeters. Likewise, the green rectangle on the right-hand side, upper corner, had a height of 2 centimeters, width of 1 centimeter, so that was also 2 square centimeters. And then finally, the square in the bottom right, it has height and width 1 square centimeter. All those add up to 5. We represent that as delta A equal 5. We notice that the change in the side length was 1, so we denote delta L equals 1, and we observe that originally L was 2. The average rate of change in the area between the side lengths of 2 centimeters and 3 centimeters is 5 square centimeters of area per 1 centimeter of side length. Learning task 2. A square with side length 3 centimeters has an area of 9 square centimeters. If the side length is increased by 1 centimeter, how much does the area change, and what is the average rate of change in the area? This is very similar to what we just did, except now we're starting with a square of side length 3 centimeters. Pause the video here and work the learning task. Your solution should be similar to what I've shown here. When the square has side length 3 centimeters, increasing the side length by 1 centimeter increases the area by 7 square centimeters. That is, if L equals 3, delta L equals 1, then delta A equals 7. We can see where that 7 comes from. We've got 3 square centimeters in the rectangle on the bottom left. We've got 3 square centimeters in the rectangle on the top right. And finally, on the bottom right corner, we've got that square with area 1 square centimeter. The average rate in change in area between the side lengths of 3 centimeters and 4 centimeters is 7 square centimeters of area per 1 centimeter of side length. We notice this is different than the first problem we solved, where that change was 5 square centimeters of area. Now we move on to learning task 3. A square with side length of 3 centimeters has the area of 9 square centimeters. If the side length is increased by delta L centimeters, by how much does the area change, and what is the average rate of change in the area? Again, very similar to learning task 2 and 1. The distinction here, though, is that rather than increasing the side length by 1, we're increasing it by delta L, where delta L can be any value. Pause the video here and work the learning task. When a square has side length 3 centimeters, increasing the side length by delta L increases the area by 6 times delta L plus delta L squared centimeters. Let's see where that comes from. If we look over on our square, we can see that the side length is increased by delta L centimeters, and delta L times 3 gives us 3 delta L for the area of the rectangle in the bottom left. Similarly, the area of the rectangle on the top right is 3 delta L. And finally, the area of the square in the bottom right corner is also delta L squared, square centimeters. The average rate of change in the area between side length of 3 centimeters and 3 plus delta L centimeters is delta A. If we add up all those areas in the salmon colored region, we get 6 delta L plus delta L squared, square centimeters of area, per delta L centimeters of side length. By calculating the delta A over delta L, that is the change in area, over the change in side length, we determine the average rate of change in area is 6 plus delta L square centimeters of area per 1 centimeter of side length. Learning task number 4. A square with side length L centimeters has an area of L squared centimeters squared. If the side length is increased by delta L centimeters, how much does the area change? What is the average rate of change in the area? Again, this builds on learning tasks 1 through 3. Now we are using a variable to represent the side length, as well as a variable, delta L, to represent the change in the area. The thought process is identical to what we've done on those prior learning tasks, except now we are doing the task more abstractly and solving every single possible square in one problem. Go ahead and pause the video here and work the learning task. Your solution should look similar to this. When the square has side length L, increasing the side length by delta L centimeters increases the area by 2L delta L plus delta L squared square centimeters. We can go over to our diagram and look at that square, and the bottom right corner has area delta L squared. The rectangle in the bottom left corner has area L times delta L. The area of the rectangle in the top right corner has area L times delta L, square centimeters. The average rate of change in the area between the side lengths of L centimeters and L plus delta L centimeters is delta A, which equals 2L delta L plus delta L squared square centimeters per delta L centimeters of side length. By calculating delta A over delta L, we determine the average rate of change in area is 2L plus delta L square centimeters of area per 1 centimeter of side length. Learning reflection. What are the pros and cons of using variables such as L and delta L instead of numbers to represent a quantity and the corresponding change in the quantity? If working with variables such as L and delta L makes it difficult for you to make sense of the problem you're trying to solve, what strategy could you use to simplify the problem to deepen your understanding of the problem? Matter of fact, if you look at how I've constructed this presentation, learning tasks 1, 2, and 3 were all designed to help you understand the problem deeply such that when you got to learning task 4, you would be prepared to be able to solve it. Consider that as an example as you write your learning reflection. Pause the video and complete your learning reflection now. As we continue our conversation, we need some additional information, specifically some additional mathematical machinery. And that machinery is limit at a point. If a function f of x is defined for all values of x near c, then the limit as x approaches c of f of x equals L means that as x approaches c, f of x approaches L. We say the limit exists if L is a finite number, and approaching c from the left and the right results in the same value of L. So here's an example. We have learning task number 5. From the graph of the function f, determine the value of the limit if it exists. This is a rather crazy looking graph, but let me just talk through what each of these questions is asking. So limit as x approaches 1 of f of x equals, what we are looking at here is if we go over to the value of x equal 1, we're looking at what the function values are getting close to as the x values get close to 1. Similarly, for the other ones, we're looking at what's going on as x approaches 2, 3, 4, and 5. Pause the video here and work the learning task to determine what value, if any, the function is approaching simultaneously from left and right. From the graph of the function f, we were able to determine each of these limits. First of all, we observe that as we move from the left, from 0 towards 1, our function is approaching 2. Similarly, as we move from the right, from 2 towards 1, we observe the function is also approaching 2. So therefore, the limit as x approaches 1 of f of x is 2. Now let's look at what's going on as x approaches 2. We can see that as x approaches 2 from the left, the function values are approaching 1. However, as we approach 2 from the right, moving from 3 towards 2, we can see the function values are approaching 0. So from the left, we're approaching 1. From the right, we're approaching 0. Because those are two different values, we say the limit does not exist. Moving on to the limit as x approaches 3. We can see as that we move from 2 to 3, that the function value approaches 1. Likewise, as we move from 4 towards 3, the function's values also approach 1. Therefore, the limit of f of x as x approaches 3 is in fact 1. At 4, approaching 4 from the left, we see that the function values are going from 1 and they're approaching 0. Coming from the right, we see that the function values are at a steady 2 the whole way. So from the left, we're approaching 0. From the right, the function values are approaching 2. Because those are two different values, the limit does not exist. Now, as we do the limit as x approaches 5 of our function, we observe that as x moves from 4 towards 5, the function values are staying steady at 2. As x moves from 6 towards 5, again, coming from the right now, the function values are also approaching 2. So from the left and from the right, we're approaching 2. Now, when we get to 5, the function drops down to 1. But that doesn't concern us. We're not worried about what's going on right at 5. We're just asking as we get infinitely close to 5 what's going on. We can see from the left and the right, we're approaching the same value, which is 2. Learning reflection. In order for a limit L to exist at x equal a, what must occur with f of x as x nears a from the left and from the right? Also, if f of a is undefined, does that mean the limit of f at x equal a does not exist? Provide 2 examples to justify your answer. Pause the video and work this learning reflection. Learning task number 6. When the side length is L, at what rate is the area changing? In mathematical terms, what is the limit as delta L approaches 0 of delta A over delta L? This is referring back to those earlier learning tasks when we were looking at the area of the rectangle, area of the square and how it changed based on the change in the side length. Go ahead and pause the video and work this learning task. When the side length is L, the area of the square is changing by 2L square centimeters of area per 1 centimeter of side length. This is referred to as the instantaneous rate of change in the area. We see that there. We have the limit as delta L approaches 0 of delta A over delta L. That's the same as the limit as delta L approaches 0 of 2L plus delta L. And as we let that delta L get as close to 0 as we want, we know that the overall limit will end up being 2L. So learning task number 7, we're letting the function be f of x equals x squared. Your task is to find the instantaneous rate of change in f at x equal a. Go ahead and pause the video and work the learning task. Let f of x equal x squared. Find the instantaneous rate of change in f at x equal a. The first thing I do is I evaluate the function at f of a. So f of a equals a squared. Next, I make a small change in the value of a, represented by delta x. So f of a plus delta x equals a plus delta x squared. I expand that out and I get a squared plus 2 delta x plus delta x squared. And to calculate the instantaneous rate of change, I look at the change in the output over the change in the input and assign a limit as delta x goes to 0 to the front. So the instantaneous rate of change is the limit as delta x goes to 0. We do the difference between the two output values You can see there that a squared plus 2a delta x plus x squared minus the a squared. The a squareds cancel out. All of the remaining terms have a delta x in them. That will be very helpful as we move to the next step. We can see that we can divide each of the terms in the numerator by the delta x. That gives us 2a plus delta x. And then we let the value of delta x get as close to 0 as we want. And we know that as we do that, the overall function is going to get it closer and closer to 2a. This is essentially the area problem we'd solved earlier, but it's generalized to be for any function of the form f of x equals x squared. That is the conclusion of this module video.